Welcome to the next lecture. In this lecture, we'll talk about the theories of covalent bonding. So in this lecture, we'll discuss valence bond theory and orbital hybridization. Next, we'll talk about modes of orbital overlap and types of covalent bonds. Finally, end the topic with molecular orbital theory and electron delocalization. So let's start with valence bond theory. What is the basic principle here? Is that the basic principle of valence bond theory basically states that whenever you have a covalent bond formation, the orbitals of the two atoms will overlap and a pair of electrons occupy the overlapping region. So this is the main idea behind the valence bond theory. So it's the space here formed by the overlapping of the two orbitals can accommodate a maximum of two electrons, and these electrons must have opposite paired spins. So this is obviously the common theme here. And the greater the orbital overlap, the stronger the bond. And the extent of this overlap depends on the orbital shape and direction. So for example, if you take hydrogens, so each hydrogen has one electron, and when they combine together, the spin changes for one electron, resulting in the overlap region. The same thing happens when you have a hydrogen fluoride. Here the valence electron is in the 1s orbital. For fluorine, the valence electron is in the 2p orbital. So when they combine, you get a region like this. When you have two fluorine atoms, again, two fluorines have 2p orbitals empty. So that results in 2p orbital overlap. Now, the orbitals that form when you have this bonding are generally different from the orbitals in the isolated atoms. So if there is a no change that occurs, then we could not account for the molecular shapes that are observed. So this here is an example or a classic example of mixing. So where orbitals mix together and become hybrids. So when bonding occurs, so these hybrids are called hybrid orbitals, and the spatial orientation of these hybrid orbitals basically corresponds to the observed molecular shapes of different atoms. So this is how we know that valence bond theory has some value to its predictions. Now let's talk about the features of these hybrid orbitals. Number one is that the number of hybrid orbitals equals the number of total orbitals mixed. And the type of hybrid orbitals formed varies with the type of atomic orbitals that are mixing. And finally, the shape and orientation of a hybrid orbital maximizes the overlap with the other atom in the bond. So let's consider that we have a 2s orbital and a 2p orbital. When they combine together, you end up getting a hybridized sp hybrid orbital, which is going to result in the formation of a linear angle, which is about 180 degrees. So what is happening here is that the 2s orbital and the 2p orbital will combine together, where the electron in the 2s orbital, one of the electrons in the 2s orbital will go to the 2p orbital, and the combined orbital formation results in the formation of sp hybridized orbital. So this is the hybridized beryllium atom that we are looking at. So in terms of the shape, the molecule will gain, for example, if you have two chlorines on the 2p orbitals, in the 2p orbitals have one electron each, so they can bond with the sp orbital of beryllium, forming BeCl2. So this is the orbital structure, the linear structure of BeCl2 that can be explained by this. The next one is sp2 hybrid orbitals. So here we have 1s orbital and 2p orbital. So we call this sp hybrid because here you have 1s orbital and 1p orbital mixing together. When you have sp2, you have 1s orbital and 2p orbitals mixing together to form 3 sp2 hybrid orbitals of boron. So this results in the formation of a trigonal planar structure where each sp2 orbital will bond with the 2p orbital on fluorine, resulting in the formation of BF3. Next, we have sp3 hybrid orbitals, where you have 1s orbital and 3p orbitals combining together, creating 4 sp3 hybrid orbitals, and each of them will bond with, if for example, this is an example of a hybridized carbon atom. Each of these orbitals, sp3 orbitals, will bond with the 1s orbital on hydrogen and create the structure of methane, CH4. And this results in the shape of a tetrahedral shape, which is the common structure shape that you generally see. Next, we have sp3 for NH3. For NH3, what happens here is that even here you still see sp3 hybrid, but here one of the sp3 hybrid orbitals is already a filled one. This filled one is called as the lone pair, and the lone pair does not bond with anything else. So here remember that the lone pair itself does not bond, even though it still has sp3 hybridization. it does not have the same shape but rather has a trigonal pyramidal shape. Next one we have for H2O, you will see the same sp3 hybridization as well in H2O, but here rather than having one lone pair, it has two lone pairs here, but still ends up forming sp3 hybridization where two of those sp3 hybrids are lone pairs. So these two are lone pairs, resulting in the formation of a bent shape for the oxygen, the atom here. The next hybridization is the sp3d hybridization, where you have the mixing of one s orbital, three p orbitals and one d orbital, resulting in the formation of 5 sp3d hybrid orbitals. And each of them here, for example, if this is phosphorus, when you see each sp3d orbital bonds with the 2p orbital, 3p orbital of chlorine, resulting in the formation of PCl5. So this results in the shape of the trigonal bipyramidal. Next one is sp3d2 hybridization, where you have one s orbital, 3p orbitals and 2 d orbitals, resulting in the formation of 6 sp3d orbitals. This is a common structure for a sulfur, so sulfur generally undergoes sp3d2 hybridization, resulting in the formation of sp3d2 orbitals. Each of them bonds with fluorine, resulting in the formation of SF6. So sp3d here, sp3d2 results in the SF6 and the shape is octahedral. So combining everything, now we can see the base structure here. So for sp hybridization, the structure is linear. For sp2 hybridization, the structure is trigonal planar. When you have sp3 hybridization, the structure is tetrahedral. When you have sp3d hybridization, the structure is trigonal bipyramidal. And when you have final sp3d2 hybridization, that results in the formation of an octahedral arrangement. So this here is the idea behind the type of orbital and the shape that it can form. So let's start, how do you define from molecular formula to the hybrid orbital? So first we start with the molecular formula. From the molecular formula we draw the Lewis structure. From the Lewis structure we calculate the molecular shape and electron arrangement. And the molecular shape and electron arrangement defines the hybrid orbitals. So whenever you see sp, this is a common example for AX. So AX2 is a common example for linear orbitals. You also have the same orbital difference for AX3 here, or AX2E. For sp3 you have AX4 or AX3E or AX2E2. All of them are tetrahedral sp3 hybridized. You also have trigonal bipyramidal for AX5, AX4E and AX3E2. For octahedral you have AX6, AX5E and AX4E2. So these are the molecular arrangements and the corresponding hybridization that results from that particular molecular arrangement. So defining the molecular arrangement, molecular shape and arrangement can show you what type of hybrid orbitals exist inside the structure. So let's take an example of methanol. So let's take methanol here. So this is the Lewis structure for methanol. When you look at carbon here, carbon bonds with 4 atoms. So here it generally bonds with 4 atoms and it's surrounded by 4 atoms. So it has an arrangement of AX4, which is the resultant shape for tetrahedral structure. So the carbon here is tetrahedral, and because it's AX4, we know that for AX4 the hybridization is sp3. So the carbon here undergoes sp3 hybridization. Let's take oxygen again. Oxygen has 2 lone pairs and 2 bonds. Again, that still gives you the arrangement AX2E2, which is also going to give you the same sp3 hybridization. So, but rather than having a tetrahedral shape, it has a bent shape. The next one is sulfur tetrafluoride. When you take sulfur tetrafluoride here, it has, when you draw the Lewis structure, you get 1 lone pair and 4 bonds. So this is a common structure for AX4E. So AX4E results in the highest hybridization of sp3d, so which is the formation for SF4. so which results in a trigonal bipyramidal shape for sulfur hexafluoride, sulfur tetrafluoride. Now, this hybridization here is not always consistent with the observed molecular shapes. For example, this is particularly true for when you have bonding of large atoms. So, when you take the bond of H2S, it's close to the angle between unhybridized p orbitals. But the d orbitals here do not hybridize effectively with s and p orbitals, which are of much lower energy and more stable. So, it's more stable to have sp, sp2 and sp3. So, these are a little more stable. But sp3d and sp3d2 are rather less stable. Next, let's talk about the types of covalent bonds. So there are mainly two types of bonds that we will discuss. One is a sigma bond, the other is a pi bond. A sigma bond is when the orbitals undergo end-to-end overlap. Now, all of the single bonds are generally pi bonds. All single bonds are sigma bonds, and a pi bond is where the bonding is sideways overlap of the orbitals. So a pi bond is always weaker than a sigma bond because sideways overlap is less effective than end-to-end overlap. So for example, if you take, where do we see pi bonds here, is you will see more commonly in double and triple bonds. So a double bond contains one sigma bond and one pi bond. A triple bond contains one sigma bond and two pi bonds. So this is how we can differentiate in terms of the bonds here. So what is an example of a sigma bond is where you have orbital overlap, one orbital overlapping with the other. So this is an example, a classic example of a sigma bond. What would be a pi bond here? Pi bond is a structure where you have unhybridized orbitals that bond sideways, resulting in the formation of a pi bond. So a double bond here results in the formation of one sigma bond. So this is the sigma bond, and the double bond here, the pi bond here, is the orbital overlap of this. So where the upper region has one region and the down has one region. This here is an example of a pi bond. So when you take acetone, acetone has rather not one pi bond but rather two pi bonds, where you have two sets of 2p or 2p orbitals that are unhybridized, which end up bonding sideways, resulting in the formation of two pi bonds and one sigma bond. So you rather have four lobes here. So two lobes for each of these pi bonds. Now, in terms of the electron density, the higher the bond order, the more the electrons are pushed towards the bond here. So the highest electron distribution is for the triple bond, and the lowest electron distribution is for the single bond. But a double bond here is generally less than twice as strong as a single bond, because always a pi bond is always weaker than a sigma bond. So however, when you have, in terms of the bond order, the single bond generally has a bond order of 1, a double bond has a bond order of 2, and triple bond has a bond order of 3. Now, so they're asking us to determine what would be the hybridization of each of these atoms here. So let's try and do this here. So let's try this one atom by one atom. First, let's look at carbon here. It has 4 bonds. So in total, and there is no lone pair, so this is gonna be sp3 hybridization. The carbon here has 1, 2 and 3 bonds and has no lone pairs here. So this carbon has sp2 hybridization, and the oxygen here has only a double bond. So this is gonna result in the formation of an sp. So there are 2 lone pairs as well and one single atom. So it also undergoes sp2 hybridization. Notice that there is 2 lone pairs, so it basically creates AXE2, so which is going to be sp2. And here this carbon here has 4 bonds and no electron pairs, so this becomes sp3 hybridization. So this is how we can lay out the hybridization for the atoms. Now what happens when you have a pi bond is, because notice that in a sigma bond you do not have a problem with the rotation. Notice that the structure is not limited in terms of the rotation, so which means that this bond can actually rotate. So there is an actual chance of rotation because the molecule is not restricted. But when you take a double bond or a triple bond, the problem in a double bond or a triple bond is that they create 2 lobes on the top and bottom, which can restrict the rotation. So which can restrict the rotation of the bond, the single bond. So which means that these are stuck, resulting in two structures, what we call cis and trans. Cis is when the adjacent groups are the same on the same side. If the adjacent groups are on the opposite sides of the plane, we can call that a trans structure, provided that we consider this as the single plane. So the plane is the one that passes through the central atoms. If they're on the same side of the plane, we call it a cis molecule. If they're on the opposite sides of the plane, we call it a trans molecule. Next, let's come to the last topic, molecular orbital theory. Now, the combination of orbitals to form bonds is generally viewed as what we call a combination of wave functions. So we use the term atomic wave functions to explain the molecular wave functions. So atomic wave functions combine to form molecular wave functions, and the addition of these atomic orbitals, also the atomic wave functions, creates a bonding molecular orbital. So which generally results in a region of high electron density between the nuclei. Now this is when you have addition. When you have subtraction, it can create an anti-bonding molecular orbital which generally has a node or a region of zero electron density between the nuclei. So think of these as a structure where it does not end up creating a bond. So that's why the name anti-bonding molecular orbital. So think of this as two waves that are combining together. If the two waves are in a phase, then the waves will reinforce together, resulting in the formation of a higher node. But when you have two waves in the opposite direction, they cancel each other, resulting in the formation of a node which is of lower amplitude than usual. So when you have two hydrogen atoms that mix together, there are two chances that it can happen. One, either it can add together to create a bonding molecular orbit, or they can subtract each other, creating an anti-bonding molecular orbital. So but depending on the type of structure that you end up with, you always have two choices for the atom. If the atom does not have a chance to, if the atom does not have an easier out, so then it will bond. If there is a higher number of electrons, then it will undergo anti-bonding molecular orbital. So we generally use a molecular orbital diagram, just like an atomic orbital diagram, to show the relative energy and the number of electrons in each molecular orbital. So the molecular orbital diagram also shows the atomic orbitals from which the molecular orbital is being formed. So for that we can calculate the bond order. So bond order is the half of the number of electrons in the bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbital. Let's take the molecular orbital diagram for hydrogen. So we have two hydrogen atoms that are combining together. So these two hydrogen atoms that combine, the atomic orbitals combine to form a bonding molecular orbital of lower energy. Remember that bonding has lower energy, anti-bonding will end up having higher energy than the hydrogens themselves. So here you have a hydrogen bond order. So you have each electrons will always fill. So when you take the electrons here, so you always fill the one with the lower energy first. So we have two electrons. So first we fill the lower energy one, and there are no more electrons left. So if there are any electrons left, then we will fill the higher energy orbital. So from this we can write the hydrogen bond order is half of, there are 2 electrons in the bonding orbital and 0 electrons in the anti-bonding orbital. So you end up with 2 minus 0, which results in 1. So the hydrogen bond order is 1. So how do you place the electrons in molecular orbits? First, molecular orbitals are filled in the order of increasing energy. So a single molecular orbital can hold a maximum of 2 electrons as long as they have opposite spins. And the orbitals that have equal energy are generally half filled with spins parallel before pairing the spins. So when you have a molecular orbital configuration, it shows the type of molecular orbital and the number of electrons in each that contain them. So for example, for hydrogen, we write it as sigma 1s taken square. So signifying that the bonding orbital has 2 electrons. So let's start with helium now. So let's start with helium 2 plus. So helium here you have 2 electrons on each of them, and on another one you have only 1 electron left. First we fill the one with the lowest energy, then we'll go to the higher energy one. Now we know that this is the one that has the structure. So when you calculate the bond order for this, we have half of 2 minus 1, so which is going to be half of 1, so which is going to be half. So when you write the structure, we write half 1s, sigma 1s taken square, and sigma 1s star. So the star signifies that it's anti-bonding, so power 1. So when you write the same for helium bond order here, so we can write we have 2 electrons on each of them, and when both of them bond together, so you have first fill the lower energy and then go to the higher energy. So when we write it as sigma 1s square and sigma 1s star square. And when you calculate the helium bond order, it is half of. So in the bonding orbital we have 2 and the anti-bonding orbital we have 2. So we end up with 0. So whenever you see a bond order of 0, it means that there is no bond. So there is no bond formation in that structure. So use the same principle now and try to determine the molecular orbitals for H2 plus and H2 minus. So let me draw for H2 plus. So where we have one hydrogen and the other one is H plus. So first we have to draw the energy. So this is gonna be 1s, this is 1s, and this is sigma 1s and sigma 1s star. So first we fill the orbital with the, well, let's check the atoms. So one is hydrogen and the other is hydrogen plus. So there is one electron here and there is one H plus here, which means that there is no electrons left here. So first we fill the electron here and there is nothing left to fill. So we generally write down the structure directly. So how would you write the configuration here? In sigma 1s, there is 1 electron, and sigma 1s star, there is 0 electrons. And when you calculate the bond order, is half of the number of electrons in the molecular bonding orbital, so which is 1, minus the number of ones in the anti-bonding, which is going to be 0, so which will give you a bond order of half. So use the same principle now for H2 minus. So H2 minus represents one hydrogen and one hydrogen minus, where you have one electron on one side and you have 2 electrons on the other side. So use this now and try to draw the molecular orbital diagram. Now let's talk about when you have higher orbitals, when you have diatomic atoms. So diatomic atoms results in the formation of either a sigma bond or a pi bond. For example, when you have 2s and 2p mixing together, you can end up with a structure that results in a sigma bond, which is going to be of lower energy than that of a pi bond, and you have a pi star, which is going to be of a lower energy than sigma star bond. So where you have 2 orbitals in the sigma bond, 1 orbital in the sigma bond and 2 orbitals in the pi bond. So this is how we can split when you have diatomic molecules. So this is how it would look like when you start filling up the electrons there. And notice that oxygen is an atom that ends up with, so the one way we can know this molecular orbital occupancy also indicates some specific properties of the material. So whenever you have the orbitals that are unfilled, when you have unpaired orbitals, it results in the bond order. Whenever you have, it becomes paramagnetic. So if the bond energy here again, when you start noticing that as you go higher and higher, you start noticing the materials become more and more paramagnetic. So oxygen is an example of an atom where you have single electrons, unpaired electrons in the pi orbital, which results in a paramagnetic properties. And you have boron, which also has unpaired electrons in the pi orbital, which makes it paramagnetic. So paramagnetism always comes due to unpaired electrons, unpaired orbitals, or unpaired electrons. Let me call it that way. So paramagnetism is a property of unpaired electrons. Whenever you have unpaired electrons in an orbital, that results in the formation of paramagnetic properties. So this is how you know the paramagnetism. So this is an example of the paramagnetic, this is a diagram that shows the paramagnetic properties of liquid oxygen under really low temperatures when poured on a magnet. So with that we end our lecture on theories of covalent bonding.